Hello everyone, and welcome to today's webinar on sensitivity analysis and Monte Carlo simulations using Simulink design optimization. My name is Aditya Baru, and I work with the controls team here at the MathWorks. In today's session, I'll be showing you how you can use the new sensitivity analysis tool to explore your design space and identify the most influential parameters in your model. Let's take a look at the agenda today. We'll begin with a quick introduction of what Simulink design optimization is, and then give an overview of sensitivity analysis. We'll then cover two examples. The first will show you how to use sensitivity analysis tool to explore your model's design space, and the next example will show you how you can use the tool to improve the performance of your response optimization or parameter estimation session. So let's start with a quick overview of Simulink design optimization. It provides you with functions and interactive tools that let you tune your Simulink model parameters to match test data. This is what we call parameter estimation, or to meet design requirements like step response characteristics, body magnetic constraints, etc. And this is what we call response optimization. The sensitivity analysis tool, which we'll be focusing on today, is a new feature introduced in our latest release, R2016A. So what exactly is sensitivity analysis? Its general definition is the study of how uncertainty or variability in the model output can be attributed to uncertainty or variability in its inputs. In the context of Simulink, we perform global sensitivity analysis to help you understand how variations in model parameters influence behavior. For example, if you have a Simulink model to describe the temperature of a heat exchanger, sensitivity analysis will help you determine which model parameters impact the temperature the most and how they do so. You can then monitor and tweak those parameters to ensure your heat exchanger is performing as per your requirements. Basically, once you know which model parameters matter more than others, you can use this information to increase reliability and robustness, reduce costs, and improve performance. For our first example today, we'll be looking at a rectifier-amplifier circuit implemented using Simscape electronics components. Our objective is to analyze which circuit components, such as resistors and capacitors, the circuit output voltage is most sensitive to. We can then use this information to ensure that the more important components in the circuit use high precision devices to meet requirements like what the magnitude of the output voltage should be or how much steady-state error is allowed. Let's switch over to the model in Simulink. Our input is an AC voltage source which is converted into a DC voltage using this full bridge rectifier. The capacitor C smooths the rectifier output, and this voltage is then amplified by the op-amp. Let's run the model to see what the output voltage looks like. As you can see, it oscillates around 70 volts. We start by opening the sensitivity analysis tool from the analysis menu in Simulink. Our first step is to identify which parameters we think have an impact on model behavior. To do this, we create a new parameter set and select the variables R and C from the rectifier circuit, and R1 and R2 from the amplifier circuit. Our next step is to create a large number of samples that do a good job of representing our design space. The design space for a model is the set of all possible values its parameters can take. In this model, it corresponds to the values of C, R, R1, and R2. The samples we create can either be in fixed intervals or be randomly generated. In case of fixed interval samples, we'll need to provide the list of values they can take. In case of randomly generated samples, we need to provide some information regarding each variable. In the Generate Random Parameter Values dialog, we first need to enter the number of samples we'd like to generate. I'll be creating 50 samples, but you can generate more if needed. The next thing to do is specify the sampling method and then define the probability distributions for each parameter. This distribution defines the range of values for each parameter. For example, in our model, we can say that the values of resistance available to us for R1 are between 9000 and 11,000 ohm, and that these values are distributed uniformly. That is, all values of resistance are equally likely to be available. We do the same thing for R2, except that its values vary between 90,000 and 110,000 ohm. We can also specify a normal distribution in case we know that the components available tend to group around a certain value. In our case, let's assume that the parameter values for R and C are normally distributed about the initial values we have defined in the model. We can then define the mean and standard deviation of these parameters as shown. So let's say that the capacitor C has an average value of 47 nanofarad with a deviation of 5 nanofarad, while our resistor R has an average value of 4700 ohm with a deviation of 300 ohm. If your parameter values are known to have some dependence on each other, you can specify the correlation as well as the extent of it. You can also use other probability distributions in case you have the statistics and machine learning toolbox installed. Now click OK to generate the samples, which are then displayed in a table. You can visualize the sample set using a scatter plot, which you can access from the Plots tab, or by simply right-clicking on the parameter set here. You can use the scatter plot for visually inspecting your sample set to see if it covers the design space well enough. You can also use it to detect correlation, remove outliers, and perform other kinds of analyses. The plots along the diagonal are histograms showing how the samples for a particular variable are distributed. So we've now specified the variables whose impact we're interested in, and also created a set of samples that adequately represent our design space. Our next step is to define the model property or behavior whose sensitivity we're interested in. In this case, we'll be looking at the output voltage of the circuit. We're interested in seeing what affects the maximum value of the output voltage, as well as how quickly it reaches this value. We'll refer to this second property as the rise time or the output voltage. So let's start by defining these two parameters as our requirements. The first requirement for the maximum value of the voltage is defined pretty easily. We'll be using a signal property type of requirement here. In our case, we'll be using the signal maximum property. We then add the signal to which this requirement applies by selecting it from the model and importing it. We're using the signal maximum property here, but as you can see, there are a lot of others to choose from depending on your use case. Once created, you can rename this requirement as shown. Our next requirement looks at the rise time, or how quickly the output voltage approaches its final value. We define this requirement as a custom one. We want to minimize the rise time and have written a function in MATLAB that lets us calculate the rise time from the output voltage waveform. This function is named rise time filter. It accepts an input argument named data, which contains information about the signal the requirement applies to, which in this case is the output voltage. We then use the step info function from the control system toolbox to calculate the rise time of the voltage. After we've specified the function for our custom requirement, we specify the output voltage signal to which this applies. You can essentially create any kind of custom requirement you want using signal data from your model and MATLAB's technical computing capabilities. For those of you who are familiar with Simulink design optimization, you may have noticed that the other requirements in this list mirror those found in the parameter estimation and response optimization tools. This helps you easily transition from working in one tool to another. Later on in today's session, I'll be showing you how you can do that. Coming back to our circuit model, we've now defined our sample set as well as our requirements. The next step is to evaluate our model for all these samples. When you click on Evaluate Model, a number of scatter plots appear which are updated automatically, with each red dot showing the new point being plotted. What's happening here is that Simulink is simulating the model using each row in the sample set as an input, calculating the maximum voltage and the rise time values for that particular simulation, and then plotting these values. As we have two requirements, we can see that there are two groups of plots. The top one for the maximum voltage requirement and the bottom one for the rise time requirement. The four scatter plots in each of these groups correspond to our parameters of C, R, R1, and R2. The scatter plots show the value of the maximum voltage and rise time along the y-axis and the value of the resistance or capacitance along the x-axis. The histograms being generated on the right show the distribution of the maximum voltage and rise time values. Let's wait for a few seconds while the evaluation is completed. By the way, I haven't sped up performance in this example, but will show you how to do so in the next one. So to quickly recap what we've done so far, we've created a set of samples, specified two characteristics for our circuit's output voltage, and will now analyze the results of this evaluation to determine which parameters have the greatest influence on behavior. Okay, the evaluation is now complete. So let's take a closer look at these plots, starting with the rise time requirement. In case of R, R1, and R2, it doesn't look like there's any kind of trend showing how the rise time changes with an increase in resistance values. However, when we look at the plot for capacitor C, the rise time increases monotonically with an increase in capacitance. This indicates that the rise time has a very clear dependence on the capacitor C. Now let's look at the plot for the maximum voltage requirement. We see that for R and C, there doesn't seem to be any trend in how the maximum voltage value changes. But for R1 and R2, we can definitely see one. The voltage value tends to decrease with an increase in R1 or with a decrease in R2. The extent of this impact also seems to be limited by these two bands here. We can take our analysis one step further by calculating statistics such as correlation, regression, and partial correlation using the raw data. This creates a tornado plot in which our parameters are ranked by their influence. Here, we can see what we already suspected from our visual analysis. The maximum voltage value is inversely proportional to R1 and directly proportional to R2. R and C don't seem to have much of an effect on this requirement, but in case of rise time, the capacitor C has the greatest influence, while the other resistors in the circuit don't have much of an impact. For those of you who are familiar with electrical circuits, the results here shouldn't surprise you. The gain of a non-inverting op-amp is given by 1 plus R2 over R1, while the smoothing capacitor value determines the waveform of the rectifier output. So even though the answer in this case may have been obvious to some of you, the approach I've shown here will apply to any kind of model, whatever its complexity. So you've seen how you can identify which parameters in a model impact behavior the most. So how can you use this information? Well, in this case, if we assume that our most important requirement is to have a small rise time, we now know that we should use a capacitor with a smaller value. And if maintaining a steady maximum voltage is more important, we can use more expensive and higher precision components for R1 and R2. So far, we've seen how you can use Monte Carlo simulations and sensitivity analysis to explore your design space. Now let's see how you can use it to improve response optimization and parameter estimation performance. We'll be using the documentation example for estimating the parameters for a muscle reflex model. The model describes the force exerted by the knee when an impulse is applied to it, like what happens when a doctor strikes it with a small hammer. Our objective is to find parameter values which most closely match our test data, and we'll be using sensitivity analysis to find a way to improve performance by reducing the estimation time for the process. The input signal provided by the signal builder block here shows you that there's a small force applied at 0 seconds and a slightly larger one applied at 2 seconds. The output of the model is the force exerted by the knee, and it's modeled as a mass, damper, and spring system with a feedback loop that has a delay. We also have access to equipment that has actually measured the force exerted by the knee for our input. It's shown in blue over here. We can see that while our model does a good job of getting the general shape of the output correctly, the parameter values we've initially defined don't match the test data very well. So our objective is to then identify the parameter values which would match this test data with the least possible error. If you were to perform the parameter estimation task as usual, it takes around 30 iterations to find the solution. And seeing how we're estimating 7 parameters, this process takes a while on account of the multiple function evaluations. And in case you're trying to estimate even more parameters or meet more than one requirement, the process might take even longer. Sensitivity analysis helps you identify a good initial point for the optimization process and which parameters are more important than others. A good initial starting point makes all the difference in an optimization process. And if we find out that 3 or 4 parameters have a much bigger impact, we can just estimate those parameters instead of all 7. We start by opening the sensitivity analysis tool from the parameter estimation session. When we do so, we need to specify which variables and requirements we want to analyze. We'll select all of them in our case, as we'd like to see the impact of all the 7 variables we have. This opens the same tool we used in the previous example. We can see that the parameter set has already been created with the 7 variables we previously specified. And our test data, which we were trying to match as closely as possible, has also been imported as a requirement. Our next step, as before, is to create a set of samples that represent our design space. The Generate Random Parameter Values dialog has already used our initial estimate of the parameters to populate the probability distribution fields. In case you want to expand the scope of your search for a good starting point, you can change these fields to cover a larger design space. For now, we'll assume that the initial ranges suggested by the tool are good enough and we create 50 samples. As the test data matching requirement has already been imported here, we can go straight into evaluating our model. In the scatter plot that's being populated, the y-axis this time refers to the error between the test data and the model output. The tool runs the Simulink model for each row in the sample set, calculates the error between the test data and the simulation result, and plots that error value. The lower the error, the better the fit that particular row of samples provides. A quick note on the kind of sensitivity analysis we've performed so far and will be performing in here as well. Using Monte Carlo simulations, we're performing global sensitivity analysis. A global analysis helps us understand how our parameters interact with each other and explore a larger design space at the same time. Now let's get back to our muscle reflex model. To improve performance, I've enabled Simulink's fast restart feature, which avoids compiling the model for each simulation. We can also enable parallel computing by going to the Options menu here. Let's wait for a few seconds while it completes evaluating our sample set. By the way, you may have noticed that some of the samples have a very high error. So I need to ensure that the magnitude of this error doesn't skew our statistical analysis later. With the evaluation complete, let's begin by finding a good initial point for our optimization process from the simulated results. We can search for a sample to be our starting point in two ways. The first is by interactively selecting a sample using the brushing tool, which is then highlighted in the table. In this case, however, all the good samples are very close to each other, and it's hard to tell them apart. So instead, we sort the evaluation table results. Here, we see that one of the rows has a pretty low error to start with, so we extract that particular row's values by right-clicking on it and selecting the Extract option. This creates a variable in the Results tab here, which will be our starting point for our next parameter estimation session. Now that we've identified our starting point, our next step is to identify a smaller subset of parameters out of the 7 we started out with. We can try and look at the scatter plots to see if we can identify any kind of trend, but that's hard to do in this case. So we use the Statistics tab in the tool, just like we did in the rectifier circuit example. This time, we'll calculate the correlation, regression, and partial correlation between the parameters using ranked data instead of the actual data, as we want to discount the magnitude of error for each sample. From the tornado plot created, we can see that the variables k, b, j, and alpha have a larger impact than tau, beta, and td. So to quickly recap, we've now identified a good starting point for our optimization process, as well as the smallest subset of parameters to estimate. We can now move back to the parameter estimation app as shown. We need to specify the initial point we'll be using, as well as the test data we're trying to match. In the parameter estimation tool, we can see from the Select Parameter tab that the values of the variables have been updated. We then uncheck the less important parameters we identified previously so that we don't estimate them. Now let's start the estimation process as we would in any other case. We can straight away see that the initial fit is a pretty good fit to begin with. And because we're estimating 3 fewer parameters, we need fewer function evaluations as well. As a result of which, we find a solution pretty quickly. And even though we were estimating just 4 out of 7 possible parameters, we still find a very good fit to our test data. So in summary, sensitivity analysis has helped us find a good initial starting point for our optimization process, and also identify a smaller subset of parameters. So we've covered what sensitivity analysis is and how it can be used to explore your design space. This in turn helps us improve the reliability and robustness of our designs. We then saw how sensitivity analysis can be used to improve the performance of response optimization or parameter estimation tasks. It does so by finding a good initial point and reducing the number of parameters to tune. That's it from me today. Thank you all for attending today's session.